Hello guys, today in this video we will start the circular motion, and in this video especially we will discuss all the basics of circular motion. So when we say a circular motion, then its definition is when a particle moves in a plane such that its distance from a fixed point or a moving point remains constant throughout. Then this motion is called as circular motion with respect to that point, and that fixed point is called as the center of that circle. So you can see this circle. So if this particle is moving in such a way such that its distance from this point O is always constant, which is the radius of the circle, so this particle would be said to be in the state of circular motion with this point O as its center of the circle. So this is the basic definition of circular motion, and there are some variables of circular motion, and the most primary and fundamental variable is angular position. Now what is angular position? So it is the angle made by the position vector with respect to the origin with the reference line is called the angular position. So I am telling you that if this is a reference line, this x-axis is a reference line, and the particle P was initially at this point. So the theta which is the angular position was 0. So as the particle will start to rotate in anti-clockwise sense, then at some instant of time this particle will be making an angle of theta with this x-axis measured in anti-clockwise direction. Then this theta will be the angular position of this particle P. If this particle P is at P dash, so its angular position will be theta plus delta theta. If this particle is at this point, then its angular position would be 90 degree. So similarly, the angular position is the initial angle which is subtended by that particle, position vector of that particle which is in the state of circular motion with the reference line. Now it is always important to note that any angle which is measured in anti-clockwise sense, theta, when measured in ACW, is taken to be positive, and theta when measured in CW is taken to be negative. This is a basic sign convention of theta which is also used in mathematics, primary mathematics. So this angular position will depend on the choice of origin and the choice of the reference line. So obviously we can say that this angular position is measured by the reference line, and that reference line also contains the origin. So this angular position will depend on the choice of origin as well as on the choice of the reference line. The angular displacement. Now the angular displacement is the angle through which the position vector of a moving particle rotates in a given time interval, and that is called as the angular displacement. So in this same diagram you can see that when at some time t this particle is at point P, and its angular position is theta. Now after some additional time of dt, this particle is at position P dash, which is at a displacement of delta theta from P, which means that in time dt this particle has moved from P to P dash, and by angular displacement of delta theta. So this is actually the angular displacement is the change in angular position in some time interval. Okay, now this angular displacement depends on origin, but it does not depend on the reference lines. Obviously if this origin is shifted to this point, this angular displacement will be somewhat different. But you can see that if this is a reference line, then this angular displacement would be same, because if y-axis would be the reference line, then the particle has moved from P to P dash, then also the angular displacement will be delta theta. Because this is a very simple thing, that difference of any quantity is in fact not absolute, and it does not depends on the choice of origin, because we are calculating the difference. So this angular displacement also is independent of the choice of reference line. Now this angular displacement is a dimensionless quantity. It does not have any dimension, and it is the rare quantity which has no dimension, but it has some unit, which is radians. Its unit is radians. Now this is a very important point to note, that about the vector and the scalar form of this angular displacement, that very small angular displacements, which are infinitely small, are following the commutative law of vectors. And commutative law of vectors is the fact that a vector plus b vector is equal to b vector plus a vector. This is the commutative law of vectors. Commutative law. Of vectors. So very small, infinitely small angular displacements follow this commutative law, but the bigger angular displacements do not follow this commutative law. So when we are concerned about very small, infinitely small angular displacements, then we can say that those angular displacements are vector quantities, but finite angular displacements, which are large enough, are not following the commutative law, hence they are not the vector quantities. So when you are writing the vector or scalar quantity about that angular displacement, you should be very careful that in the numericals angular displacements are not so small, so that you can refer them as a vector. So we take the angular displacement as a scalar quantity. Now, although this angular displacement is not a vector quantity, but then also it has a definite direction. Its direction is governed by the Fleming's right hand screw rule. So just imagine that there is a particle which is revolving in a horizontal circle, and you are watching that particle from top, and it is revolving in the horizontal circle anti-clockwise. Now if you rotate the fingers of your right hand in the sense of rotation of the particle, that is in the anti-clockwise sense, and you point your thumb straight towards upside, then your thumb will be representing the direction of angular displacement. So this is the Fleming's right hand screw rule, that if you curl your fingers along with the circular sense of the motion, then the thumb which is straight opened will be pointing towards the angular quantity, which is either angular displacement, angular velocity, or angular acceleration. So this has a definite direction which can be governed by Fleming's right hand screw rule, and I have explained that in the first figure. You can see that if the particle is rotating anti-clockwise sense, then if you curl your fingers along the sense of rotation, and you open your thumb straight opened, then your thumb will be pointing towards yourself, and this dot will represent that the angular displacement would be towards the observer who is watching this diagram. But if the particle is rotating in clockwise sense, as you can see in this diagram, then if you curl your fingers, right hand fingers, along with this clockwise sense, then your thumb will point inside the plane of the screen, and therefore this cross will represent the angular displacement. Now moving further, the relation between angular displacement and the linear displacement. We know that in any circular motion, the length of the arc and the angular displacement theta and radius are related by the formula theta is equal to arc upon radius, and arc is equal to theta into radius. So this arc length L will be equal to theta into r, and this is the relation between the linear displacement, which is this arc length, and the angular displacement, which is this theta. Now the angular velocity. Angular velocity is the rate at which angular displacement changes, and this is also a vector quantity, because the instantaneous angular velocity is d theta by dt, where d theta is a very small angular displacement which follows the commutative law. So it is a vector quantity, but the average angular velocity is a scalar quantity, because that is equal to the change in angular displacement upon time taken for that change. And this theta 2 minus theta 1, in fact this theta 2 and theta 1 are the big enough quantities so that they are not being a vector quantity, because they do not follow commutative law. So the average angular velocity is a scalar quantity, while the instantaneous angular velocity is a vector quantity. Now the direction of angular velocity is also determined by the Fleming's right hand screw rule, which means that if any particle is rotating in an anti-clockwise sense, then the direction of angular velocity will be towards the observer coming out of the plane, and if the particle is rotating in the clockwise sense, then the direction of angular velocity will be away from the observer, perpendicular and inside the plane. Now the linear relationship between angular velocity and the linear velocity will be calculated here. So we know that L, which is arc, is equal to theta into radius. Now if we differentiate with respect to time on both sides, then dl by dt is equal to d theta by dt into r, and this dl by dt is linear speed v, and this d theta by dt is angular speed omega, and r is the radius. So if we need to find out the vector relationship between them, then in the vector form, v vector is equal to omega vector cross r vector, and this is not equal to r cross omega, because there is a difference of negative sign. To avoid the confusion of omega cross r or r cross omega, you can understand by the Fleming's right hand rule that we when we say that c vector is equal to a cross b, then you should determine the direction of c vector by Fleming's right hand rule. If a is written before b, then you should rotate your right hand fingers starting from a towards b. I'm telling you again that if a is written before b, then you should rotate your right hand fingers starting from a vector towards b, and you should observe your thumb, which is wide straight opened. Then your thumb will be representing the direction of c vector, which would be perpendicular to a and b both. So in the similar way, if v vector is equal to omega cross r vector, then we can verify this result, that v vector is towards this direction, and omega is towards yourself, because it is coming out of the plane, because the body is moving in a anti-clockwise sense. So if you start your fingers with the direction of omega, that is out of the plane, and if you will take it towards the direction of r, then you will see that your thumb will be pointing towards the velocity, this one. So this is omega, which is coming out of the plane. Then your finger should be starting in the direction of omega, then it should be pointing towards, it should be moving towards r, then your thumb will be pointing towards v. Similarly, in the next diagram, the omega is inside the plane. So if your fingers are starting from the direction of omega, which is inside the plane, and you are rotating it in the direction of r after omega, then your thumb will be pointing towards v. Now the angular acceleration. due to the fact that instantaneous angular velocity is vector quantity itself. Therefore, both average angular acceleration and instantaneous angular accelerations are the vector quantities, because instantaneous angular acceleration is itself d omega by dt, while average angular acceleration is change in angular velocity, change in instantaneous angular velocity upon time taken for that change. So the instantaneous angular velocity is vector quantity, therefore both of these angular accelerations are vector quantities. So it is the rate of change of angular velocity is known as angular acceleration. The unit of angular acceleration is also radian per second square. Now there is a very important thing about the angular acceleration. The angular acceleration does not depend on the sense of rotation. In fact, it is in the direction of the angular velocity if the angular speed is increasing. Like in a similar way, that if we are moving in a straight line and our speed is increasing, then acceleration will be in the direction of our velocity. And if we are moving in a straight line with a decreasing speed, then our acceleration will be pointing in the opposite direction of the velocity. So if the angular speed is increasing, then the angular acceleration will be in the same direction of that of omega, angular velocity. But if the angular velocity, angular speed is decreasing, then the angular acceleration will be in right away, the opposite direction of the angular velocity. So there is some analogy between linear and circular motion, that in linear motion the first equation in motion is v is equal to u plus at. In circular motion it is omega 2 is equal to omega 1 plus alpha t, where omega 2 is the final angular velocity, omega 1 is the initial angular velocity, and alpha is the angular acceleration. Now like s is equal to ut plus half v square, this theta angular displacement is equal to omega 1 t plus half alpha t square. V square is equal to u square plus 2s, then omega 2 square is equal to omega 1 square plus 2 alpha theta. P is equal to mv, where p is momentum and m is mass and v is velocity. Therefore L is angular momentum, I is the analogous of mass, which is moment of inertia. It would be discussed in the rotational dynamics, and this omega is the angular velocity. The kinetic energy here is half mv square, and here it is half I omega square, where I is the moment of inertia, which is analogous of mass, and omega is analogous to v. Thank you.